the exam, April 16th or 17th, you should have gotten an email from Pat Thompson about that. That's the one where you, just for showing up, you get $50, and if you score in the top 50%, you get $20 more. So that is open to everyone in calculus at ASU, all classes of calculus, and they're only taking 300 people. So please sign up for that. Sign up for that before the cap is reached. Okay? Your question, yeah?
Will they like email you back?
Yes. If what?
Well, like because if you like register it, then I'll email you and say like.
Like a confirmation?
Yeah.
I'll find out.
Okay.
But yes, there should be something like that, or else I'll find out what kind of confirmation you get. But yes, respond to that email, and if you didn't get that email, let me know, and we'll get you the information. Okay? So $50 guaranteed, right? 70 if you do well. Yeah, just top 50%. All right, any questions about that? Okay, so we're working on line integrals of vector fields. Well, both kinds, but we left off with vector fields last time. So we're going to work on these today. So I've got these two. I've got two paths in two different fields. And these paths start and end at the same place, and we call those line integrals circulation integrals. And sometimes you'll see a little circle on the integral. That's what that means. That means you're making a closed loop around, and that's what both of these are. And so it's the same path. So I've got like a triangular path, and then there's a unit circle, path around the unit circle. And these two, do the vectors show up? Let's turn the grid off. Hold on. Let's see. Yeah, that's fine. That's fine. Are they faint enough to see them? Like to? Okay. Let's see. Oh, right here. Let's try light blue. How about that? Yellow. I don't know. It's not my favorite shade of yellow, you know. So just gone with blue. Okay, so we'll do that. All right, there we go. So same. Graph paper off on this one. Okay, so what we want to do is we want to be systematic about this, and we're going to basically find these four line integrals. So what does it mean that, like, we got this triangle and we make these abrupt turns? What will that mean for the line integral? If I want to do the line integral around this path, what will that mean for the calculating it? Yeah, we're going to have to do it in pieces, right? We're going to have to parameterize each piece separately and add up the three integrals, okay? So, but in terms of parameterizing, we don't have to do that once, and then we just apply the different field to the same path. Okay, so I want to give you in terms of parameterizing a segment, I want to give you a technique that's really convenient, so we're going to go, we're going to clockwise around this. Yeah, we'll go clockwise around. And so we'll call our blue one C1, and we'll call our red one C2. And then we'll have like C1A, C1B, and C1C, or something like that. So in terms of C1A, which is this first part of C1. C1 is the whole thing. C1A, then it's just this diagonal. So when you're parameterizing a segment, there's something that's really helpful, so that your starting point is assigned to t equals 0, and your ending point is assigned to t equals 1. Because with a line segment, there's infinitely many ways we could parameterize it. Okay, but what is the one parameterization that gets us t equals 0 for this point and t equals 1 for this point? Then once we have that parameterization, we set up the integral, then we just write 0, 1, 0 to 1, right? So that's convenient. So what you can do is, so this is for C1a. T. So let's do variable t. So we're all doing the same thing. We'll do variable t for this first one. Then we'll do variable u on C1b. And we'll do variable v, TUVs on C1c. Okay, and then for C2, let's use TUVW. Okay, so we have a different parameter for all our different individual parameterizations. So then so this isn't right here. I'm parameterizing in one variable, right? I'm doing a path, so I just want t. So what's this technique? So when t is 0, I want to get what point? I want to get 1, 1, right? So let's put that down. So I want to get 1, 1 when t is 0. So then I'm going to have this is linear, right? So it's going to be some coefficient times t plus some coefficient times t. So the question is, what are those? So here, when you plug in t equals 0, the coefficient times t goes away, and we get the point 1, 1. See how that works? So now when I plug in t equals 1, I want to get what point? I want to get -1, -1. So really what I need here is for the x, I just need how much x changes. If I do how much x changes, because I'm going to multiply by 1, right? So my starting 1 plus how much x changes times 1 will give me the final x. So how much does x change? -2. Okay. So I'm going to go 1 plus -2t. And that way, when I plug in t equals 0, the plus sign. When I plug in t equals 0, I get 1. And when I plug in t equals 1, I get -1. It's because I have the start plus the amount of change. So what will it be for y? My starting value of y is 1. How much change? How much change in y from there to there? Also -2, right? They're both -2 in this case. So if you do your starting point plus the amount of change to get to the final point, then when you plug in t equals 1, it'll be starting plus change will be final, right? And so this will get me 1, 1 at t equals 0 and -1, -1 at t equals 1. So that's just a convenient technique for that. You don't really need that on vertical and horizontal lines. I'm going to let you guys do that on your own. So that's kind of easier if you. So, but just when you have lines that aren't horizontal or vertical, this is a nice technique. But what are you going to do? So you're going to continue by parameterizing C1b. And we said that was going to be in terms of what? U. And then do C1c. In terms of v. And then parameterize C2 in terms of w. So you're gonna and then you're gonna set up 4 line integrals, right? So the line integral for C1 in this field on the left here, negative 2y, and then the same path, C1 for negative 2x, and then C2 for negative 2y, and C2 for negative 2x. So we're going to write out 4, and don't do any simplification. We'll let the computer do the solving for us, but we're going to just set up the line integrals so they would be ready to solve as a basic single integral. So do all the work so that it gets to the point where you got a basic single integral. So there's a lot to do there. Take maybe 10 or 15 minutes. I can come around and help, but it's just good practice. And then we're going somewhere with these examples with a new concept. But this is, in the meantime, this is really good practice for single line integrals. Okay. The dot product for this diagonal part of C1. Here's that integral. See if you agree with that. Did anybody get that?
What? So, right, and then DR. So you just take the yeah. No.
Agree with that? At least one does?
Yeah.
Yeah? Lots of people do. Good. All right. So then this next one. So on the vertical and horizontal lines, so the x coordinate's always -1. And then you could just make y u, and then just your limits of integration would just be the y coordinates start and end. Instead of having to do this 0 to 1 thing, it's easier. You could just do -1 u, and then just integrate from what? -1 to 1.
Wait, so when you start at 0 and go to 1, when you set t equals to 0?
You could do it that way. So if you're talking about this next
Yeah.
part. Yeah, you could do it this way where you force u to be 0 here and u to be 1 here. But that's kind of, in these vertical and horizontal lines, it's kind of like more work. It's like, just make it u, and then just, when you do the integral, you just go from the starting y coordinate to the final y coordinate. But you could absolutely do that. Do u equals 0 here and u equals 1 there. It works. Because for a line, there's an infinite number of ways to parameterize it. So as long as you parameterize it correctly and then choose the right limits of integration for how you parameterized it, it's fine. But I think for this is the easy. Just call y equal to u, and then make your limits the y coordinates of start and finish. Yeah?
Wait, so how do we know when to use -1, 1 for C1b and C1c, and then just for C1x we use 0, 1 as starting points?
Okay, so I recommend making the 0 to 1 on some kind of slanted line. But if you have a horizontal and vertical line, you can do it that way. There's an infinite number of ways to parameterize a line. But I think the easiest way for a horizontal and vertical line is to just let the y coordinate, if it's vertical, be your parameter, and let the x coordinate be the parameter. And then just make the limits of integration the x and y coordinate.
All right.
Does that answer it?
Yeah.
But yes, you can, if you want to finagle it so that u equals 0 gives you this point, and u equals 1 gives you that point, and then integrate from 0 to 1, that's perfectly fine.
All right.
Like the way we did it on the slanted one. Did I answer the question?
Yeah.
Okay. All right, so now, so is this, are we good on this first one? All right, so the next one goes from, so we got to move here, we can get through this. Okay, so now the next one, we're going to do the field, which is -2y times 0, 1. So do you just get, so we're going to do the derivative of this, and we get 0, 1. And this is going to be -2u. So I think it's just u. Is that right? After you do the dot product, you just get u. If you're doing it my way?
Yeah.
And then the limits of integration will be from what to what? -1 to 1. So this is y equals -1, which is what I called u. So -1 to 1. If I lost you, please ask. Yeah.
So I get you to the dot products just to get u, but I'm confused on how it just becomes like u alone.
So it was dr would be 0, 1, right?
Yeah.
dr is 0, 1. And then my f is -1. No, -2y. But what is y? Y is u. So the dot product is u.
Okay.
See it? Are we good? All right, last one then. So parameterization is? Oh, v1, right? So dr is 1, 0 now. And I've got -2, 1. Dot product, -2. And that goes from what to what? -1 to 1 again. So that should give me a value. Please give me a value. It does. So now I put that all in. I got it right, and it told me that sum of those triple integrals is 0. So going around that loop, accumulating all the vectors along the way in the direction of the path, we get a 0. If this was a force field, and it would be 0 amount of work to go around that loop. Okay, what about for C2? So how'd you parameterize C2? Sine, comma, cosine? Cosine, comma, sine. All right, that's the most convenient way to do it. So C2, cosine W, sine W. And then dr would be negative sine W, cosine W, is that right? Yeah. And so for this one, we're doing -2y, which would be -2 sine W, would be f. If f is -2 and then y, which is y is sine W, what is our dot product? +2 times sine of W plus cosine W times sine W. And that's from what to what? 0 to 2 pi. (5.8 times 10 to the -16th). It's telling us what? 0, right? 0.000, 16 zeros or 15 zeros, and then 6. It's essentially 0, right? It's doing some numerical method to calculate this, but it's giving us like a little bit of error in its method, right? A teeny itsy bitsy bit of error. It's really telling us this is 0. Okay. Questions on those first two? Okay, these. So I'm just gonna. Who is confident about their integrands here? Kristen, are you confident? Can you tell me? Now this is doing for -2 comma x.
Yeah, so that one, from 0 to 1, I got -2 times -2.
Again, okay.
Plus -2 times 1 minus 2.
Okay, so it was the same. That's almost the same as the other one, or the same?
The other ones I did from 0 to 1, and so it would be -2 and then -4.
Did somebody else get this? So now it's the same path around the triangle, adding together these three. Someone else get that?
Yeah, this should have been the middle one. It should have been not -1 or -2, but should have been 2 times.
Did anyone do it the -1 to 1 way? Anybody home? Anyone confident about what they did? What's that? Here it's -1? Okay, so that's the same as this. If you do -1, -2 from 0 to 1, that's the same as -1 from -1 to 1. Okay, so so this is right. And this one, are we on the same page here? Do you go -2 from -1 to 1? And this last one?
I didn't like it.
Okay, sorry.
Figuring it out. Yeah, I got -2, so that works.
So you got -2 from -1 to 1?
Yeah, so that's
Okay, so this is right. This is correct. All right, so there's that. And then, last one. Going around the circle in this field. So now it's still, so what do we got? Now -2x, so it would be -2 cosine W. So what changes here?
the second.
Just the second half?
Yeah, just that sine changes to cosine squared.
Cosine squared. Great. Okay, so so what do we conclude here? So notice for these two loops around here, the line integral was 0. For these two loops over here, the line integral was not 0. So does the picture of the vector fields, first of all, agree with that? So if we were to make a loop around here, so look at the C2. If we were to make a loop around here, does it look like it should be a 0 line integral? Why? Because in the first half, the vector field gives help, right? In the second half, it's symmetric, right? It's symmetrically opposite of what the field did in the first half. So we could have predicted that'd be 0, and then likewise for the triangle, we could talk about this looks like positive, this looks like 0 and negative, right? So this is 0 along here, negative along there, positive mostly along there, so looks like we have some cancellation effect there. What about going around the loop in this one? Tell me, what's the work, positive or negative? Through here, positive, positive, positive. And what about through here? There's a kind of a 0-ish area here, a little bit negative down here, a 0-ish area here. Net result? Positive, right? Is that what we got? For that C2 in the second? Yeah, positive 1.647. Okay? So what's going on here? Why did those two loops give 0 and these don't? It's because of the field. We call this, so what happens is, as we go around, the work that the field does to help us here going is the same work that kind of like we put back into the field down here. So what you have is the idea of conservation of energy. So this we call a conservative vector field because energy is conserved as you go around a loop. Energy is not conserved here, right? So the work that the field does is positive as we go all the way around. So this is not conservative. We don't have conservation of energy as we go around a loop. So now the question, what is it that makes that one a conservative field and this one not a conservative field? Why is that one a conservative field and this one is not conservative? Any ideas? Something we've talked about.
The vector field is symmetrical.
Okay, it has symmetry. But even if I did a loop down here like this, where it's not symmetric, that still would give a zero integral. Anything special about this negative 2y? A characteristic that this doesn't have, negative 2x? Anyone remember? Yeah? Okay? Yeah? Is that what we're going to say? So negative 2y, is negative 2y a gradient field? Can we write a function f(xy) that has negative 2 as the x derivative and y as the y derivative? What would it be? Negative 2x plus y squared over 2. What about this? Are we able to write a function that has negative 2 as the partial with respect to x and x as the partial with respect to y? Let's try. What would we try? We would try with negative 2x plus xy. Is negative 2 the partial derivative with respect to x of this function? No, it'd be negative 2 what? Plus y. We need a plus y here. We don't have a plus y. It's impossible to write a multivariable function that has this as its gradient. It's impossible. There is no function that has negative 2x as a gradient. So this is a quality of gradient vector field. So this is a gradient vector field, negative 2y. Gradient vector fields are conservative. Non-gradient fields are not conservative. And we'll pick it up there on Friday.